Thank you for the introduction, and thank you to the organizers for inviting me. It is not my first time in Vienna. It's not even my first time here, although it's my first time speaking here. I hope it won't be too chaotic. It might get a bit. I'm sorry if that happens. Tim earlier said he was nervous about speaking here. If Tim needs to be nervous, I need to be downright terrified. Because he knows a lot more about mean curvature flow than I do. And I'm going to talk about mean curvature flow, or I'm going to start with mean curvature flow. Let's put it like this. A lot of the people earlier today introduced essentially all of the notions. So I will be fairly quick with the general setting. I'm going to be interested in the mean curvature flow of networks. What is a network, or a regular network for me? Well, I have a bunch of embedded curves, sufficiently regular. It doesn't really matter in my talk how regular they are, because they're going to be smooth anyway. And despite my terrible drawings, these should all meet at 120-degree angles. I'm going to consider them in R2, and I'm going to consider them on the whole space. So some of these curves might very well be infinitely long. So my curves are going to be gamma I. They are going to be, I'm going to parametrize them on some possibly infinite intervals into R2. And I assume that everything is parametrized by arc length. I'm also going to need the normals. Usually I'm going to talk about the normal Ni being defined as the derivative of gamma I and then rotated by 90 degrees counterclockwise. So say if this is gamma 1, this is gamma 2, this is gamma 3, then if I do this, my normals look, so this is N1, N2, and N3. And you can express the 120-degree angle condition as a condition for the normals, except that, okay, here in this picture, the expression at the triple junction here is actually the sum of the normals. But yeah, since I'm fixing orientations of the curves, I have to be careful at the triple junctions. If my normals are coming from outgoing curves, I really want a minus everywhere. And when a curve is incoming, I want a plus. So don't worry too much about it. There are sign issues with going in and out of triple junctions. So for the Herring angle condition, I always want outgoing normals to sum up. Okay, so in the talk of Salvatore, we already saw that the central notion is that of a self-similar shrinker. Because these arise, or these can arise if you do a parabolic blow-up in a singularity of the flow. And let me directly write it down. So curvature on the curve gamma I to me is gamma I double prime dot Ni, and then the shrinker equation is that the ith curvature should be equal to minus gamma I dot ni halves. And if you look at it, this tells you that, well, the curvature is equal to the normal component of the curve. So there is no time here. If you would let this evolve by mean curvature flow would just be shrinking everything via homothety. And this is then one of the time slices. As you shrink, you should adjust the number down here. There are various conventions around for what number you put here. That just corresponds to fixing the time slice. Don't worry about it. Right, and we haven't really seen too many examples of solutions of this. So let me give you a couple of them. Let me start with the ones we've seen or essentially seen. First one is just a straight line going through the origin. The origin is a special point for this equation because, well, your curves are supposed to be moving by just dilations, right? So dilations mean the origin is important. So you have the line or lines. You have triple junctions where the origin is at the center. You have a circle, and the circle has to have a specific radius. In this case, square root of 2. If you plug everything up there, you realize that's what it gives you. And then there are a bunch more where maybe some more interesting things happen. So there's Brackespoon. Network like this appeared in Salvatore's talk, where as one of his bad configurations that he needed to, at least topologically, that he needed to rule out. Right, there is a singularity that looks like this. Then there is the lens. There is the three-ray star. Origin in the middle. And then there are a bunch of others. There is the four-ray star. There is a five-ray star. There is something called the rocket. And there is one called the fish. I hope I didn't mess the labeling of these up the labeling of these two, but I don't think so. Okay. Then there is. So these are due to work by Chen and Wu in 2007. These are the only ones, the only solutions with at most one chamber. Well, this is a paper in the physics literature. It is the arguments seem correct to me, but I'm not quite sure if I would consider the paper being really rigorous. Yeah. Yeah, of finite mass. Also, they didn't consider this one because they didn't consider it physical. You know, they were interested in the evolution of grain boundaries, and well, for them, this and this would be the same phase, so there would be no interface there. But okay. Now, if you're interested in which ones of these actually arise in physical situations, the next question is well, which of these are stable? You would only expect stable self-shrinkers to really be observable in nature, because if they're unstable, you know, chances are you have a small perturbation of them, and then they go somewhere completely else. That's also why I didn't bother with any shrinkers with more than one finite mass chamber, because all of them need to be unstable. Basically, because there is a topological condition for how fast the area shrinks under mean curvature flow. So if you perturb, you know, if you have multiple chambers, you perturb one of them to be slightly larger than the other, you know, it will vanish later. Okay. So these are the only ones that are potentially stable. And what is known so far? I mean, the line and the triple junction are maybe not so interesting in that regard. For the circle, this was proved in the 80s, and let me quote Epstein and Weinstein, and also Hamilton, Page, and Grayson. And more recently, so especially here the later Hamilton, the Hamilton gauge Grayson theorem tells you if you start with any simple closed curve in the plane, you let it evolve, it vanishes, and you know, it shrinks into a round sphere, into a round circle. Well, that would be a form of, yeah. So that would be a stability statement. Recently, a group around Julian even proved that you have weak strong uniqueness for solutions starting close to the circle up to the point of the singularity. So the circle is fairly well understood. Brachis-Spoon stability here was shown by Alessandra. And for the lens stability was only known under symmetry assumptions. And there are two works, one by Azuani et al. The rare case of a math paper where I don't want to write down all the authors because that's too many to write down. And then there is Bellettini and Matteo in the same year. Triple junction is the three-ray star is open, and all of these guys, these are linearly unstable, it turns out. And that's due to work by Chang in 21. And that's what's known about, or what used to be known about stability of self-similar shrinkers. So what's left to do is somehow understand the stability of these guys here without a symmetry assumption and here at all. And that's what I'm going to show you today how to do, at least in the case of the lens. I claim that I'm able to prove that all of these are linearly stable in an appropriate sense. And let me show you how. So what does linear stability? So what do I mean by linear stability? It turns out that a network gamma. Did I already? So okay. So I'm going to call my networks gamma. Big gamma. Turns out gamma is a self-similar shrinker if and only if it is a critical point of, well, so let me write it down let me write down this expression for general x in R2 and T positive. But the criticality I'm going to ask for x equals 0 and t equal 1. But keeping these for a second is helpful to understand what later the result is. Self-similar shrink. You have a self-similar shrinker if you have a critical point, essentially of the perimeter in Gaussian space. Okay, I need x0 and t0 squared divided by 4t0 d h1 x. And if you recall, Salvatore's talk, these are precisely the kernels that popped up in Huysken's monotonicity formula. So in particular, we know that whenever we plug in a flow, all of these guys get smaller. So, our shrinkers are critical points of at least one choice. If we knew that, then this f would be, they would be stable critical points. So the second variation would be positive. Then that would tell you something about stability, right? Because can't go. It has to go. The flow decreases this, but if the second variation is quadratic, you would imagine you have a local minimizer. So the only thing that it can do, at least heuristically, is flow into that. But that picture has a problem, as we're going to see, or as you might know. But okay, so we have a critical point. I already said we should look at the second variation. So the second variation, fortunately, I don't have to compute that anymore because because Chang already computed it for us. So the second variation of f0, 1 is given by the following. Okay, this is due to Chang in 21, but for the smooth case in higher dimension in higher dimensions, this is due to Holding and Minikotzi. Well, so the second variation is defined on variations of my network. I'm going to write down a bit more about these in a second, but these are, so you integrate again over gamma b times w prime minus k squared plus 1/2 v w, and then times the kernel, e to the minus x squared x, if you want. And then there are boundary terms at the triple junction. I'd prefer not to write them down because I don't think they're terribly helpful for the moment. I'm going to write down what they mean for the eigenvalue problem in the second, though. So wait a second. Okay, and the W and V, they are in a space of variations, and you have to be careful here. These are not, these are not variations in physical space. They're parametrizations of variations in physical space. So I want to consider these as normal components of a variation that moves about my network. So these are on each of my curves of the network, I want H1 functions on AI minus, AI plus, with respect to the weight. So gamma I squared of t dt. And because I have parametrizations of variations, I need to incorporate the Haring angle condition, and that's if I corresponds to a curve at a triple junction small o, then you sum the orientation times ui at the triple junction, and that should be 0. The notation is a bit. I'm cheating with the notation. So here I mean evaluate the variation at the triple junction, and this is the orientation for ingoing, outgoing. It's a bit annoying in that regard. Okay, so those, and you can prove that at least if your elements in this space are smooth enough, there you can construct an honest to goodness vector field that can act as a variation of your network. Okay. Then you should get an eigenvalue problem. I'm too slow. Okay, never mind. The eigenvalue problem looks the following. So I have an operator that is defined on all the variations on my individual curves, and it is minus the second derivative plus, I think, 1/2 gamma I dot gamma I prime ui prime plus minus a squared plus 1/2 ui. And the eigenvalue problem for this is now for this operator, and so you have L of ui equal lambda ui. This is for all I belonging to the for all indices for the curve for the shrinker, and of course you want that U is in your space of variations, and at the triple junctions you need one more condition, and the condition is that U I1 e to the minus gamma I squared for derivative at the triple junction, these all agree. I1 gamma I2 squared prime triple junction is the same as UI3 e to the minus gamma I3 squared quarter prime triple junction. Right. So if you want to determine whether your shrinker is stable, you have to solve for the first couple of eigenvalues here, and then see what happens. This has the structure of a quantum graph in Gaussian space with anti-Kirchhoff boundary conditions. I'm just going to take that as it is and just sit down and solve it, or you can there is fancy you can use fancy words, but I'm going to treat it as what it is, a coupled ODE system. We also know that there are a priori that there are a bunch of eigenfunctions, namely, okay, the whole problem is rotation invariant, so there should be something, there should be an indeterminate mode corresponding to rotations, that is gamma times gamma prime, rotations. And here the eigenvalue is 0, as it should. Unfortunately, there are also unstable modes. One is dilations. So that's the curvature. This is coming from dilations. The eigenvalue is -1. And then there are eigenvalues due to translations, and that those are nu times the normal, where nu is a vector in R2. This is translations. And this is lambda -1/2. First-let looks bad. Well, I said those should be linearly stable, but and now here are unstable eigenmodes. But well, dilations for self-similar solutions correspond to slight changes in time. So okay, if you look at your shrinker slightly later, if you perturb it to be slightly later than initially, then it's not surprising that the singularity happens earlier. And if you did that, you should have really adjusted the time slice. So that's not really a problem. And for the translations, the same. If you perturb it in such a way that your singularity is slightly away from zero, same thing. You should first adjust it so that the singularity is at zero, and then you can expect stability. So the theorem is going to be, and this is something I did on my own, hopefully this year. I'm quite confident. For the lens, I have it. For the lens, these are the only unstable / indeterminate eigenmodes. Unfortunately, I don't have a lot of time anymore to show you how to prove it. Let me give you some very quick ideas. Well, first I should write down the lens. I need to parameterize it. This is gamma 1. This is n1, gamma 2, n2, and the curved arcs I parameterize like this. Questions? I parameterize like this. Well, okay. So gamma 3 and gamma 4 are both parameterized on the interval minus AA. There are 2, and this point here I call P0, and this one here is minus P0. Apparently this thing has symmetries, right? If I take the rotation Rx equal x1 minus x2, or I should write it like this, x1 minus x2, so just reflection around the axis, then some of my variations here are symmetry preserving, some of them are symmetry breaking, and the symmetry preserving ones are UD and UTE1. These are symmetry preserving. And the other two are symmetry breaking. So UTE2 and UR are symmetry breaking. And you treat both cases slightly differently. Let me quickly comment on how to do the symmetry preserving ones, even though the ones in the that would be the case corresponding to the one up there already, but somehow this case is harder in the sense that it requires you at some point to come up with an explicit number that is bigger than some other number. Here you can get away with a qualitative argument. Basically because the rotation it corresponds to eigenvalue 0, and if you can prove that, for symmetry breaking, this is the lowest eigenvalue, this is the next lowest eigenvalue, well, the one above you don't care anymore, it's positive anyway, because the eigenvalue here corresponds, this is already 0. Whereas here, if this is the lowest eigenvalue of the symmetry preserving ones, this is -1, this is -1/2. For the next one, you need to prove something. Yeah, you just know that, you would just know that the next one is bigger. A priori, you just know that the next one is bigger than -1/2. So here you have to produce a number bigger than 0. Here you just have to, prove that you can count eigenfunctions, eigenvalues, and let me. Where am I? Here. Okay. Very quickly. So if I have a symmetry breaking, a symmetry preserving, eigenfunction, then, well, if it's symmetry preserving with respect to the rotations, you can't do anything on the straight rays, right? Because if you go up or if you go down, that breaks the symmetry immediately. So you get U1 equal U2 equals 0 everywhere. And U3, symmetry preserving, if you work out the normals, actually means that U3 is equal to -U4. Bit weird, but that's what it is. Kind of. This is the variation that belongs to the first curve. This is the variation that belongs to the second curve, and so on. And if you look now at the equation here for U3, you see that because you have equalities at the for the derivatives at the triple junction, you see that for U3, this is what's called a regular. The eigenproblem is what's called a regular Sturm-Liouville problem. And Sturm-Liouville theory tells you there are countably many discrete eigenvalues that are ordered, and the nth eigenvalue has precisely n zeros. And then you look at the zeros of UD. UD has no zeros because it's the curvature, and there is a conservation law for that along the curves, along the curve gamma 3. Translation in E1 direction, well, it's translation like this. The normal component has a 0 up here that has 1 0. So that's the next eigenvalue. So right away you know that those are the two lowest eigenvalues, but then for the third eigenvalue you have to prove that it is sufficiently big. How do you do that? Well, you write it down as a Rayleigh quotient. It's in nice coordinates. It's even quite clean, and then you estimate that quite brutally, and you end up and you're lucky. For the symmetry breaking, I really don't have much time anymore. For the symmetry breaking, it's kind of similar, except that then you have to redo Sturm-Liouville theory, because you have for the symmetry preserving ones, the unbounded variation is just vanished, and I just essentially reduced everything to a single curve. For the breaking ones, I can't do that anymore, and I really have to deal with these transmission conditions at the triple junction. But still, you can make something like classical Sturm-Liouville theory work. And basically, you can count zeros on the curved arcs. Again, this one is translation up. This one does not have zeros. This is the lowest eigenvalue. Rotation. If you look at the formula again, it has a 0 in the middle. That must be the next eigenvalue. But this one is 0, so you don't care what the next. The next one must be okay. But now I'm really over time. Thank you for your attention. I hope it wasn't too messy.